Hi, I'm Steven Feuerstein, and I write practically perfect PLSQL.
Greetings and welcome to the PLSQL channel, a series of video trainings on the Oracle PLSQL language. My name is Steven Feuerstein, and I'm a PL/SQL developer just like you. This lesson is part of my series on effective management of PL/SQL-based applications, and the focus of this lesson is the Optimizing PL/SQL compiler. Okay, so this lesson is actually part of a sub-series of 3 on fully leveraging the Oracle 10G and above PL/SQL compiler. Back at the release of Oracle 10G, Oracle demonstrated its long-term and very deep commitment to the PLSQL language by providing several major enhancements to the PLSQL compiler. It essentially rewrote the entire compiler framework. It now provides automatic, transparent optimization of your code. You don't do anything, and Oracle automatically works on your code or changes your code to make it run faster. And I'll talk to you about why you should not be the least bit concerned about the fact that Oracle would make such changes. Compile time warnings gives you the opportunity to improve the quality of your code. Oracle will give you feedback, not just on whether or not your code compiles and what the errors might be, but ideas they have on how you can make your code run faster or work better or be more maintainable. And conditional compilation, in which you get to decide what code should be compiled and what code should be ignored. And Oracle 11G offers enhancements to both compile time warnings and optimizations. So these are 3 major enhancements to the way that you can run your PL/SQL code or design your PL/SQL code, and you should be conversant with all 3 of the features and know how to apply them. And what we're going to talk about in this lesson is the optimizing compiler. So as of Oracle 10G, the compiler now has the ability to automatically optimize your code. Essentially, at the time you compile your code, Oracle rearranges that code or the resulting internal representation of your code and to make it run faster. And the bottom line is that there's a clear trade-off. The time it takes to compile your code will increase, not that you'll necessarily notice, but the runtime performance will improve, and that you will definitely notice. The improvement in performance from 9 to 10G was essentially doubled. Your code ran twice as fast, making no changes besides recompiling your code, and you see even better performance improvements just by compiling into 11G. You get to choose the level of optimization. There are 4 levels as of 11G. Level 0 means turn off optimization. I don't want to take advantage of your amazing new feature. Level 1 means sure, do some optimizations, but not so much, and this will reduce the impact on compile time. Level 2 is the most aggressive, at least prior to 11G, making the maximum possible code transformations, doing all the possible arrangements that it can. And that will also have the biggest impact on compile time. So in other words, it could make your compile time go even slower. Level 3, introduced in 11G, provides automatic inlining of local sub-programs in addition to everything performed at level 2. And I'll explain what I mean by inlining, or what Oracle means by it, a little bit later in this lesson. So you get to choose, but level 2 is the default. And there should be very few reasons that you would ever want to change your optimization level from the default of 2. It's possible, I suppose, that you might have a program that for some reason takes a lot longer to compile when full optimization is turned on, but you don't get a lot of benefits out of performance. So maybe for that one program unit, you would move the level down to 1, but I think it's very unlikely that will ever happen. And certainly you might find some opportunities to get improved performance out of inlining of local subprograms. So for some of those programs, you might want to set the level to 3, or perhaps always set the level to 3. But the default of level 2 will give you the best bang for the buck. And essentially, when it comes to the optimization of the compiler, you can just stick with the default and never worry about it. Don't pay attention. So let's take a high-level view of the optimizer, understand a bit more about how it works, show you some examples, and draw some conclusions. Essentially, the optimizer takes advantage of freedoms to reorder the execution of statements. Essentially what happens is that Oracle has taken the liberty to change the route that the runtime engine will take to get from point A to point B in your code. In other words, when you write your program, you're specifying a logical algorithm, what you need the program to accomplish to meet some user requirements. The underlying implementation of how it does its job is largely hidden from view for you. Now, prior to 10G, the order of execution of your statements, or the order that the compiler follows, pretty much conforms to the order in which you wrote them. But the optimizer takes advantage of what it calls freedoms to reorder the execution of statements. Here are some examples of the kind of freedoms that Oracle takes advantage of. Unless otherwise specified, the operands of an expression may be evaluated in any order. In other words, you might have A plus B plus C. That's a commutative operation. And you could then see them being executed B first, then C, then A, or A, then B, then C, or C, then B, then A. In other words, top to bottom, left to right, no longer necessarily applies in the computation, the execution of the statements in your code. The actual arguments of a call or a SQL statement, so in other words, the values that are passed into a call to a procedure, or the binding of variables in a SQL statement, may be evaluated in any order. So the bottom line is, whoops, sorry, I don't know what happened to the rest of my statement. You need to be careful to avoid relying on a specific order of execution of arguments and so on to achieve the results that you want. And in fact, part of what the PL SQL Optimizer is doing, or will be doing, is discouraging you from making assumptions about the way your code will execute. Now, in general, PL SQL developers are not making these kinds of assumptions. They're just writing their high-level logical code. And all these details, the order of operation, the order of evaluation of expressions, the order of evaluation of arguments, these are things that you don't pay attention to. You should not have to pay attention to. And Oracle's now saying, don't pay attention to that. We're going to take care of it automatically, and we're going to take advantage of that freedom to improve the performance of your code. Let's take a look at some examples from simple to very sophisticated to give you a sense of the kind of optimizations that Oracle might perform on your behalf. Suppose I have a PL SQL program in which I have, in sequence, two different expressions, A plus B. And neither of these are changing between those statements. Oracle will or could automatically optimize this code as follows. Basically declare an internal variable. We never see the variable, but it's generated by the compiler. It assigns A plus B to T, and then it references T in both of those subsequent expressions. So again, this is invisible to us, but Oracle saves an operation. It doesn't compute the addition over and over again. Here's an example where I have a loop, and inside the loop I have an invariant. A is assigned the value of B plus C over and over and over again. So Oracle says, well, that's kind of silly. I'm going to take it out of the loop, evaluate it before the execution in the loop, and save the repeated execution of that statement. Hopefully these make a lot of sense to you, and of course Oracle does many more complex, more sophisticated kinds of operations than this, but it should give you a sense of the kind of freedom they're taking to improve the performance of our code. And last, to look at a very interesting and powerful example of specialized optimization in the Oracle environment, Oracle will automatically take cursor for loops, in which I say for every record in a specified select statement, do some stuff. It will automatically, in essence, implement that cursor for loop to perform at a level similar to a bulk collect operation. In other words, retrieve all the rows from the table in one fetch, or actually in multiple fetches with a row level or row count set to 100. Now, if you don't know what bulk collect is, then I encourage you to check out the Turbocharging SQL Performance, or bulk processing of SQL and PL SQL series of lessons. And you can learn much more about bulk collect and its partner, for all. So if you're not familiar with bulk collect, you definitely need to learn about it. But the point here is that when it comes to cursor for loops, you don't have to explicitly convert your cursor for loop into a bulk collect, because Oracle will do it for you. It doesn't actually convert it into a bulk collect exactly. It converts it into a internal code that performs like a bulk collect. Let's take a look. So the 10G optimized CFL program compares the performance of different approaches to querying data. So I'm going to test cursor performance. I'm going to pass in the kind of approach I want to take and the number of operations. Let's see, am I actually using OL? I don't think I am. That was from an earlier iteration. Let's check and make sure. Let's perform some refactoring on my code to improve it. Do I use it? No. Okay, so let's improve this program. I pass in just one parameter. And what I'm going to do is select 100,000 rows or up to 100,000 rows from my all source data dictionary view, which shows me the source code of the programs that I can execute. Then what I'm going to do is fetch the data from this cursor through three different approaches. One approach is with an implicit cursor for loop. So for every record in my cursor, I'm going to do nothing, just fetch the rows. Then I'm going to do the same thing with an explicit open fetch close. So open my cursor, fetch the next row, exit when I'm done. Again, don't do anything with the data. And third, I'm going to use the bulk fetch. So inside a loop, I'm going to open my cursor again. Inside a loop, I'm going to fetch up to 100 rows at a time. And I'm going to exit when my collection is empty. So again, this is a fantastic feature introduced in Oracle 8i actually, and it will allow you to improve the performance of multi-row fetching. But as you're going to see, when you've got a cursor for loop, it'll automatically convert it to this level of performance. So what I did then, so there's my program that compares the three approaches, and I calculate the elapsed time with my SF timer package, start the timer, run my queries, my retrievals, and show the elapsed time. Then what I'm going to do is test this program's performance with different levels of optimization. So I'm going to turn off optimization, and here's the statement that I can use to do that for a specific program. Alter procedure, the name of the procedure. I'm going to recompile it with an optimization level set to 0. Turn it off. And then I'm going to test cursor performance for implicit cursor, explicit fetch, and bulk fetch. And I'd better get rid of all these :1s. Otherwise, my program will not run. But I got rid of my parentheses too. Let's try that again. Let's just get rid of everything but the parentheses. Okay. So now I test cursor performance. I pass in the implicit cursor approach, the explicit, the bulk fetch, and then I turn my optimization level back to 2. The default. I turn optimization back on, and I run it again. Now this takes about 10 seconds to run altogether, so I'll let you do it on your own time, but I can show you the results that I found. So let's take a look. On 11.2, with optimization turned off, the implicit cursor for loop took about 3.5 seconds to fetch those 100,000 rows. My explicit took about 3 seconds, 3.1 seconds, so a little bit faster, but the variation there depends more on what's going on my computer. For example, the second time I ran it without optimization, the implicit was 2.7, the explicit was 2.8, very close, essentially the same level of performance. The bulk fetch, 0.83 seconds, so it's significantly faster than row by row fetching. But when I turn on my default optimization, so turn on the optimization to level 2, run my code again, notice that my implicit cursor for loop is now much faster than my explicit loop, and about the same as my bulk fetch. And you can see this in my several different iterations of execution. So the implicit cursor got much faster, the explicit cursor stayed slow, and the implicit and the bulk fetch are about the same. So what you're seeing here is Oracle automatically converting the cursor for loop to run as if it were a bulk collect. Now again, it doesn't actually recode the cursor for loop as a PL SQL bulk collect. What it's doing though is saying, hey, when you write a cursor for loop, you're not writing a program, you're not writing an algorithm. You're making a statement. You're saying to Oracle, hey Oracle, please fetch each row so I can do something with it. And I don't really care how you open, how you fetch, how you close, how you determine when it's time to stop. You take care of all the details for me, and I'll just focus on the high-level requirements, which is what I'm going to do with the data that I'm fetching. And because I'm not specifying a specific kind of execution path or an algorithm, Oracle can re-implement this high-level statement, this descriptive statement, however it chooses. And with optimization turned on, it chooses to execute it in a bulk approach, essentially in C code or machine code, retrieving multiple rows with a single fetch. When I do the explicit open fetch close, Oracle does not optimize this to run faster. Why not? Well, with the optimization, Oracle has to be very careful to avoid any possible side effects that could change the logical outcome of your program. And since I've taken it upon myself to define each individual step of my operations, it's impossible for Oracle to look at the rest of my code, which of course has other statements all over the place. other statements here, other statements here, and so on. Oracle cannot guarantee that by changing its approach and fetching, say, 100 at a time, that it can perform the same operations with the same logical outcome. So I've basically boxed myself into a corner with my explicit approach to fetching my data, and Oracle cannot optimize this code. But with this approach, in which I say, please fetch each row for me, and I don't care how you do it, Oracle then has the freedom to rearrange that code and change the implementation path. And the results are rather astonishing. From 3.5 seconds down to less than 1 second. So what you see here are examples of relatively trivial transformations of code, changing the way the code is executed to improve performance, and much more sophisticated and deep optimizations that Oracle performs. Either way, though, the performance of your program will improve and improve markedly. So things to keep in mind. The PL/SQL engine will always execute your subprograms, even if the optimizer detects that the results of the subprogram are not going to be needed. What do I mean by that? Well, suppose your program does something like this. It calls your function, and then it multiplies that by null. It's a silly example, but just to point this out. The result of this expression will always be null. But this function might perform some operation that is required. In other words, that it might delete rows from a table or some other side effect in your code. It's not a good idea to write these programs with side effects like that, but it's possible you could do it. And Oracle doesn't want to destroy the logical framework, the logical impact of your code. So it will call this function, and then it will likely just ignore the value returned because it knows that it should evaluate it to null. But it will always execute your subprograms. That's something you can rely on. But what you cannot rely on is the specific order of evaluation of arguments in a subprogram, or even when package initialization takes place. So when I have a package that has an initialization section, let's show you an example of that. Here's a package, employee lookup 2, that has at the bottom of its package the execution of the load cache program. This code initializes my package, and it basically populates an array with a copy of the employees table. This is an initialization section, and what Oracle is telling us is that it will decide when and if the package should be initialized. Essentially what this means is that it will try to avoid initialization if it's not really needed. For example, if I have in my package specification a type statement, type ABC is a record, and then in some other program I reference this record, so declare, or this record type, my record to be employee lookup 2 dot ABC. When this code is executed, Oracle does not really need to initialize my package, it's just referencing this type. So in that kind of situation, Oracle may decide to not initialize my package. You don't know, you don't have to worry about it, it's simply Oracle doing its job under the covers to optimize your application code. Now you can, as I've noted, change the optimization level. The optimization settings are retained on a module by module basis. Each program unit has its own optimizer setting. And every time you recompile your code with non-default settings, the settings will stick unless you recompile later without reuse settings. So let's take a look. Here's an example of altering this procedure to set the optimization level to 1. So alter the procedure, compile, optimization level set to 1. And I could also say alter session, set PL/SQL optimize level equal to 1, and that would set the optimizer level to 1 for any subsequent compilations in my session. Later on, I might want to recompile this program, and unless I include the reuse settings clause, Oracle will use the current session settings for my procedure compilation. So if I alter my session, setting the optimization level to 0, and then I alter procedure, recompile, and don't include reuse settings, the optimization level for BigProc will be set to 0. Now, as I mentioned before, there should be almost no circumstances where you ever actually need to deal with this. You will generally just rely on the default level of 2, or you might increase the optimization level to 3 as part of your general session settings, and then just forget about it. But if you ever do change the optimization level for a specific program, and you want to retain those settings, you will need to make sure to reuse the settings whenever you recompile. We'll talk about a data dictionary view, all PL/SQL object settings, in which you can check the value of your optimization level for any of your program units when we talk about leveraging data dictionary views to analyze your source code further on in the series. Let's talk about inlining in Oracle Database 11g. So this is a new level of optimization available, level 3. Inlining involves the replacement of a subprogram invocation with a copy of the invoked subprogram. And this only is relevant if the invoked and invoking subprograms are in the same program unit. Well, what does that mean? What it means is that when you call a subprogram, let's take a look at an example. Here's a procedure called show inlining that has within it multiple subprograms. These are nested or local subprograms, and they have some code in them. And I can then call my program. Here's an example of calling F2 multiple times. And the code obviously for F2 is not down here. Instead, the code is up here. So it's a way of hiding the logic for us and avoiding repetition of our code and so on, improving readability and avoiding repetition. And in fact, these local submodules are a very important feature for writing more maintainable code. And I have a whole separate lesson on write tiny chunks of code in which this feature is explored. The problem is that when I run this code, there's a small amount of overhead to find the code and then execute it. So what Oracle allows us to do is specify that we want to inline this code. And what that means is that when this code is compiled, since I've turned on inlining for F2 here, or I can even turn it on for the entire program unit as a whole, every time this program unit is encountered, Oracle replaces the function call with the function body. So this code will be repeated multiple times in my program. In other words, with inlining, my compile code gets larger because the actual code inside the function is copied into the executable section, as opposed to simply pointing to the code and then finding it at the time of execution. So that's what inlining does. It helps you avoid the overhead of making the call to the subprogram. And it's a fairly complex setting compared to the others. Essentially, when you set the optimization level to 3, available in 11g only, the compiler will seek opportunities, as they put it, to inline all your subprogram invocations. In other words, if I set my PL/SQL optimization level to 3 at the session level or for a given program unit, then every single subprogram invocation will be inlined, if it can be. And Oracle has all sorts of complex rules about some exceptions when they may not be able to inline that subprogram. But essentially, it'll seek every opportunity. And then in addition to setting your optimization level setting, you can use the pragma, the inline pragma, to raise the priority for inlining. You can say, on this particular one, I really, really want you to inline it. And then Oracle will make every effort to inline it unless there's some specific problem that precludes it from doing an inlining. And if you have your optimization level set to 2, not 3, then you can still ask for inlining of invocations of subprograms, but you have to request it explicitly. So what you're seeing here is that even if I have the optimization level set to 2, I'm specifying inlining for F1 all the time in this program. And here I'm specifying inlining of F2 for this specific statement. And I'm saying for this one, do not inline the execution call of F3. So it's a fairly sophisticated and nuanced optimization compared to simply saying, set my optimization level to 2. In my analysis, the scripts that I've put together, I have not been able to detect a noticeable improvement in performance from inlining. I think you'll see it if you do some very heavily recursive program executions or lots and lots of repeated executions of the same large subprogram. But again, my experience has not been able to demonstrate a clear benefit to inlining to optimization level 3. Chances are you will not see it either. So you could certainly set your optimization level to 3 and try running your application as a whole, see if it runs faster. Or again, you can most likely simply stick with level 2. And interestingly enough, it's possible that inlining could actually slow down your code. If you read the documentation, you'll find this warning. And the reason this might happen is that the inlining that Oracle performs occurs early in the optimization process. And it possibly later on in the process, Oracle might not be able to apply more powerful optimizations to your code because it's already been inlined. So that's why Oracle allows you to turn off subprogram inlining. If you actually find that inlining is slowing down your program unit, but you will benefit from some of the inlining, then you can use the various profiling capabilities, for example, DBMS HProf, the hierarchical profiler of 11G, to identify the subprograms that are slowing down. And then you can apply the specific pragma to say don't inline this particular subprogram. Obviously, this is an attention being paid to optimization which most of us don't have to worry about. But if you're working in programs that you have to get the performance to the highest level possible, you'll be looking for every possible opportunity. And in this case, if you're on 11G, you should take a look at the possibility of using the inline pragma and the optimization level set to 3 to get the most out of the compiler and to adjust the way the compiler works with your code to get the best performance possible. You can learn lots more about the PL/SQL Optimizer and performance in general by visiting the OTN, oracle.com/technology, their technology environment. And you'll find a number of different white papers that explore in much more detail how the introduction of the compiler optimization, lots of detail on how and why it does the optimization. So what does it mean to talk about freedoms within a language, the order of execution. And so this second white paper is by far the most interesting and most deep in terms of explaining how the optimizer works. It's written by a fellow named Charles Rutherell, who's one of the senior developers and architects of PL/SQL, and it goes through lots of detail on why freedoms exist in programs, definitions of freedoms, the side effects that can occur in your code. So if you are interested in getting more detail, a deeper understanding about how the compiler works and how the optimization process occurs, check out these white papers. You can also run your own performance analysis based on a harness that Oracle has put together to allow you to measure performance of your PL/SQL code and also analyze common myths about performance in PL/SQL. So again, if you're particularly concerned about performance of your PL/SQL code, or if you simply want to get a much deeper understanding of how PL/SQL works from the standpoint of performance, check out these white papers, documents, and resources. Conclusions. The optimizing compiler can make a big difference in overall application performance. Now, if you're new to Oracle or you've upgraded, your site has been upgraded to Oracle 10G for a long time now, this is pretty much old hat. You're taking advantage of the optimizer, your code's running faster, and it's just something you've always been used to. And it's great. And if you want to get a sense of all the wonderful benefits you're getting, try turning off the optimization level, running your code again, and see what the difference is like. Because the best thing about it is you don't have to do a thing. The default optimization level of 2 will handle almost all your circumstances. It will optimize your code. You will not worry about the improvements or the overhead of additional compile time. The inlining of 11G is probably not going to benefit you that much, so you just stick with the defaults and enjoy the performance. But you should certainly also explore the possibilities of benefits from inlining in Oracle 11G. Then just sit back and enjoy all the great benefits.